My name is Dr. Barry Blight. I'm an Associate Professor of Inorganic Chemistry at University of New Brunswick in the Department of Chemistry. Porous materials that we get to make in our lab are actually really extraordinary. MOFs are really neat because they are a class of porous solid that we can actually tune the size and shape of, kind of like building cages with Lego almost. And what's great about them is that they actually are more like ceramic materials, fancy ceramics. And so when we develop these systems, they actually look a lot like sand, fancy sand, really. And we can actually do really interesting things with them. So we can actually engineer them to have really crazy internal surface area. So that means that they can have a really large amount of space inside. For instance, 1 gram of these materials can have up to 3,000 meters squared of surface area inside. So it's like, that's just a handful of sand that has that much space inside. And that means that we can actually engineer these materials to hold a lot of things, a lot of gas or drugs or other interesting materials that we need to store or deliver. You could take a single cylinder, like gas cylinder that would have, oxygen or hydrogen in there. You could fill it with this fancy sand, and you could then put 14 cylinders worth of gas in that one cylinder that's already full. And that's just because of the way the molecules going into the pores of the sand can actually pack more tightly like Lego rather than trying to push their way out. The most effective carbon capture is that of trees, converting CO2 to oxygen, which is what we breathe. And of course, deforestation is a problem there. Well, right now, apart from this idea of forestation or not being able to build more forests or grow more forests for carbon capture, a lot of it has to do with scaling, right? So the types of materials that are required for carbon capture or for hydrogen storage are, you need a lot of it, and there isn't a lot of that material. And with the surface areas of MOFs that I described earlier, and the pore volumes that we can make use of, we can store a lot of gas with a relatively small amount of material, making use of these materials. We can actually engineer the MOFs to have specific properties. So we can actually make them with bigger pores or smaller pores, depending on the gas we want to capture or filter. We can have them have a higher affinity for CO2 or a higher affinity for hydrogen if we want safe hydrogen storage for hydrogen fuel. Luminescent materials are actually really important. So if you think about the mobile phones that you have, biosensors for biologic or for medicinal applications, your children's toys are fluorescent, right? All of these things lead to technologies that require luminescence. And so by taking advantage of this natural phenomenon, we can actually engineer materials that help us do interesting and useful things. So this is an interesting property that luminescence has, is that it's extremely sensitive. We can use a very small amount of our fluorescent material and detect as low as parts per billion of analytes in a large dilute water sample without having to use a lot of our material. This means that the fluorescent signal that we detect can detect very small quantities of analytes that might be harmful in drinking water. Because of the tunable properties that we mentioned earlier, we can actually make use of the porous solids in really unique ways. So we can build them in to host drug molecules. We can design them to dissolve over a long period of time, and as they dissolve, they can release drug molecules, which makes them really useful in terms of like long release times for particular drugs that might degrade really fast in the body. Drugs often have a profile of like action and then the decay as most of the drug gets consumed. But if you can influence not the decay of the drug use or its metabolism, how your body chews it up, you can slow that down by encasing it in something. And so as that material degrades, it then releases the drug over time. The stuff in the center of the porous solid, it'll take a lot longer to get to that than the stuff that's out on the outside. So you end up with a much longer, slower drug release profile than something that you just take and it hits and then it happens in 4 hours and then you have to take more. Well, with MOFs, you can take one that's every 12 hours, for instance. The best part about what we do is the fact that we get to bring science fiction to life. We get to make it science fact by doing our experiments and developing new materials to do super exciting and interesting things that we think will help New Brunswickers and Canadians moving forward.